Hi guys, this is a video to answer a question that one of my viewers asked. He had worked on a German radio that had what they called a shunt regulated push-pull preamps in it, and he wanted to know how these operated. A little history. I don't know where this name came from. It's also called a series regulated push-pull. It's based off of an invention in 1943 that the actual name was a balanced amplifier. The invention was actually used for, or was designed for, TV circuits and oscilloscopes using electrostatic picture tubes. These are the type of picture tubes that, instead of having a vertical and horizontal coils, and use electromagnetics to move the electron beam back and forth across the screen to paint a picture. They use, for deflection, they use plates and use electrostatic, and the amplifier was designed to drive the verticals, and we'll get into why here in a few minutes, but it never really gained a lot of popularity. Wasn't really used in much that I can find, although I think there was some oscilloscopes that actually used it. It was patented really by a designer and working for RCA. So we all know how RCA deals with anybody that's working with them and patents that come out of there. Anyway, so you'll find different names for it. Totem pole, which is what I learned it by. U-follower, cascade or cascoded cathode follower, which is another somewhat popular name, although that's really not an exact name because that's actually a somewhat different circuit. So anyway, what really are we talking about here? Well, first of all, to kind of understand how the circuit works, we're going to look at something a little different, and then we'll get to the circuit. Let's say that we've got a voltage source, and this thing comes out and feeds, and I'll use, well, we'll just draw a box here and we'll call it load. Okay, now that could be any kind of load, but it's a load. Alright, I could actually put a resistor symbol there because that's really what a load is. It can be impedance, which is AC load or AC resistance. It can be anything. But let's say, due to whatever reasons, we need to drop the voltage to this load. Alright, well, one end is going to be connected directly. In order to drop the voltage to it, one simple, quick way, an easy way, is put a series resistor in here. And that'll do it just fine. You know, we can figure out what size that resistor is. We know what the load is and what the voltage being supplied, and what we can do Ohms Law, get the current going through the circuit, and know how much voltage we want to drop, and then just do Ohms Law and figure out the resistance. And that's fine as long as this load is steady. In other words, the load don't change. And one way, one example of this is in your transformerless radios and TVs. They tie the heaters or filaments in series, and to drop the voltage from your line. across them. So you can have, some, like a 12BE6, a 12BA6, and, various different voltage filament tubes. As long as the current's all the same on each one of the tubes, they require the same amount of current. This is perfectly feasible. And if your tube count or whatever, or your line voltage, if it doesn't quite fully add up to what your line voltage is, you can put a series resistor in, drop it. A lot of TVs did this in the 50s. They went from, they quit putting transformers in, and they would tie, a lot of times, usually they had enough tubes, they ended up having to tie in a couple parallel series lines, but they would have to put a resistor in because everything didn't quite fully add up to the line voltage drop, so they had to put a resistor in there. And that's a steady load. I mean, once the tubes heat up, they draw X amount of current all the time that they're on. Fully heated up, they're going to stay steady at that current. It doesn't change, so we get by with a series resistor just fine. Nothing changes. But in this circuit, if that load would change, say B plus voltage going to a tube. Now your B plus going to your tube, the current in that tube starts fluctuating. As you put a signal in, and I mean that's how it operates. You put a signal into your grid, control grid, and what it's actually doing is controlling the current going through the tube. So consequently the current then starts fluctuating on our load. Well, when the current starts fluctuating, then the voltage drop on this series resistor is going to fluctuate. Not very stable. So how could I do this and change this to fix that problem? Well, there was one quick way of doing that. I go ahead and run this straight through. Well, not straight through. Whoops, sorry guys. I come here and I come down through a real simple, just 2 resistor voltage divider. I do this, I can keep my current relatively stable going through here. In fact, depending on my choice of resistors compared to my load, I can keep it extremely stable within a certain reasonable adjustment of this load current. Because really basically the power supply is seeing more this here, this current loop here, than it is seeing here. This current will always stay this pretty well stable, keeping the voltage drop and keeping the current through this one fairly stable, so then the load sees a stable voltage at all times. Now it's within reason. You can actually go outside, you can draw so much current or so little current that you can actually start changing the total circuit current enough that then you will get varying voltage drop. But within a certain reasonable amount, this will stay stable. And it's used considerably, especially when you're wanting to drop and have different voltages on your B plus. Maybe some of your circuits need, say, 300 volts. Maybe some only need a B plus a couple hundred volts. Some may only need 100 volts or 125. You can actually just start putting a bunch of different resistors in a voltage divider circuit there and control that. To make it a little more stable, a lot of times they'll go ahead and put some filtering caps in there. They'll kind of stable things out too. But this here is basically the same thing, except we're going to put tubes in here as the shunt regulated or series regulated push-pull amp, or also known as, or the true name of a balance amplifier. Now we'll draw out the circuit and look at it. So basically we have 2 tubes. Now this guy's going to go up here to B plus. Alright. We'll come down through here, through a resistor, to here. We'll connect off of this and come up and feed the grid. Come out here with a cap. Come through a cathode resistor. Grid resistor. And we'll have our load. We'll call that RL. Now this is a very simplified drawing of this. Now, this basically is something similar to what I had before, where I had those two resistors feeding off to my load. Put that in as a resistor. Load. Where's the bell? Kind of similar. But in this case, we're using tubes. Now, what is really going on here? Well, we feed a signal in here, input to this triode tube. And what happens, and I'll probably use a better pointer than that, what happens here is, of course, this starts fluctuating the current going through this tube, as it should. You know, you got an AC signal going here. This changes the current through this. So we get a change in current coming out, and which changes the voltage drop across this resistor. Well, coming off that plate is another line going into this tube, hooks to its control grid. So the changes here affect this, which is connected to the B plus through the whole series. What happens there, and what that allows to happen, as this fluctuates, as the input signal fluctuates the current to this tube, this will counterreact in this tube, which will keep a steady B plus and a steady current overall through the entire circuit. Now the way it does that is really kind of relatively simple. Now there's some extensive math to this if you was actually going to design the circuit, and I won't get into this because I'm just basically talking about the basic operation of it. But if this signal is going positive at this point, then coming out of here will actually be opposite, negative going, which is what's feeding this. As that becomes more negative, less current flows through, which allows this thing to be controlled with less current, which reduces some of this drop here but keeps the voltage steady. As we go the other direction, as this becomes more negative, we drop the current here, that becomes more positive, we allow more current to go through. Now this signal is being seen out here too, like this. Now one of the big advantages of this circuit, well actually two advantages. One, we keep things very steady on our B plus. The drops across the two resistors here, across our loads, across the tubes. Remember, tubes have internally plate resistance, so those have to be taken into account. we keep everything steady as far as B+. The other nice thing about this is if my B+ fluctuates, things stay steady also. We don't have to worry about it as much. So in cases of I don't want to say really TVs, because really a lot of TVs don't use highly regulated power supplies, but a lot of your test equipment like oscilloscopes do. You want to keep your B+ real steady so that throughout your entire circuitry, and especially your sweep circuits and your deflection circuits, everything stays steady so you get a true representation of wave on the tube of what you're measuring. So everything's got to stay steady. The thing that can fluctuate B+ is heavy loads. You know, this is going to go ahead and start feeding the rest of your amplifier. And in an audio sense, it's feeding audio amplifiers which draw a lot of current, which fluctuates the B+ somewhat. So this thing also, this amp will keep that signal going through very steady, even if the B+ changes and any changes internally in the circuitry here. Everything stays stable. The other advantage is it acts as a cathode follower. Now, what is so nice about cathode followers? A regular cathode follower is not much of an amplifier. It doesn't amplify. In fact, gain is less than 1. But it does allow for very low impedance, a very low impedance output. Now, to kind of explain that a little better, we need to look at some resistance or impedances. Why do I want a low impedance? This is going to feed tubes, you know, the grids of tubes. This, you know, your load will be actually a grid of the next stage of the tube, which is a high impedance. Why is that so really vitally important? Well, you need to understand one thing about load, and this sometimes becomes a very confusing thing. If I would take two loads, let's just say two resistors. Again, guys, I'm not much of an artist, so I got one resistor here and one resistor here. And this is, say, a 10 ohm resistor, and this is a 1 meg, big M, ohm resistor. Which do you think is the bigger load? Well, think about that for a minute. Is the 10 ohm a big load, or is the 1 meg a big load? Well, let's kind of look at this a little bit. If I supply both of these, either one of these, with 10 volts, in other words, I have a 10 volt drop, you know, I hook them to a 10 volt battery, and I figure out the current, because the load, the heavier the load, the more current it wants. And if I figure that out, well, then I just take my 10 volts and I will divide it out. And here I have 10 volts, that's going to equal 1 amp. Well, what about this guy? Well, that's going to be a lot less. It's going to be about 10 milliamps. Actually less than that. be about 10 microamps. There, that's better. Well, 10 microamps is an extremely small current. You know, that's 0.0, 5 zeros and then a 1. That's 1 amp. So 10 ohms is an extremely heavy load compared to 1 megohm. And that comes back to your that will come back to like your meter loading. You know, we've talked about this, you know, ohms per volt meters and stuff like that, and you know, the digital meter versus the VTVM and stuff. You know, these digital meters like a 10 megohm impedance and stuff, and so on. Okay, getting back to this, this may be feeding into a grid of a tube, and that grid could have, you know, upwards of 1 meg input impedance. If everything is relative, so if I'm feeding a high impedance with a low impedance, as far as this circuit is concerned, the lower its output impedance is, the higher this appears as far as its input impedance, and less load that it is. So the lower I can get this, the bigger difference between these two, the less current I'm going to draw from this, and the more steady this whole circuit becomes, and because of the less current, and I can actually drive this tube with a lot more voltage and still keep my current levels real low. And that's what I want. To drive an output tube, and it could be even an input, another preamp stage going before it gets the output tube. But to drive that, if I want to get a lot of power out of this, I want a pretty decent large swing, in other words, very large swing in my voltage. But I don't want to have to supply a lot of current to that. Because if I have to supply a lot of current with that amount of voltage, it's a lot of heat, a lot of wattage draw, which is going to drag my B plus down, which is also going to work these tubes. If I can keep this real low impedance respect to this, this becomes a very, very low, not very heavy load, a very low load, because of the difference between the impedances or resistances, and which means then to drive it with this high voltage, peak to peak, big swings, won't take near as much current. I don't draw as much current through here. B plus stays stable. These tubes stay happy. Everybody's staying cool. And I stay linear. Meaning that this output going into there will be, if it was 100% linear, then it will be identical to the input. And when it, in other words, basically the only difference between the two would be just that it's amplified. But otherwise, the waveform looks identical other than it's larger. That's linearity. And in order, one way of definitely guaranteeing good linearity is keeping this tube, this preamp, operating at low current. And in order to do that, the best way is a cathode follower. But I get the cathode follower here, but I also get amplification here. A normal cathode follower has no amplification. In fact, it's less than 1. But if I can get amplification and the low output impedance of a cathode follower, then I've got something. But again, that explains what it is. The operation of it basically is you're running from here to here is your power supply. This basically goes to ground. You have a current flow through this. When this fluctuates, this does just the opposite, keeping that current steady going through here at all times. Steady current means for linearity, keeps everything operating in a linear fashion within reason. And also any fluctuations in B plus will be met with staying stable too, because fluctuation in B plus will not affect this circuit because of the fact that it's fed the way it's fed. Because of this connection in the series fed with the cathode to the plate that's coming up here, controlling this tube with respect to this tube. And it's called a push-pull because that's what it's operating as. One pushes, one pulls. Back and forth, depending on where the wave's at. What's going positive or it's going negative. But it's just push-pull. I hope that explains some of it. You know, I try to keep this in a short, short video. So much for that. I tried to keep it very simple. The biggest thing to realize is whatever's going in here is fluctuating right here. As this fluctuates, the current through this tube changes and fluctuates, which then is the opposite effect up here, which keeps the total stable. The current flow through the total thing. So, you know, one way to kind of look at it, in a perfect world, you could say that, say this current in this tube is fluctuating by, say, 10 milliamps. Then really technically this one is doing the same thing. But as this current goes, say, negative 5 milliamps, then this one will go positive 5 milliamps, making up for it. So the overall current stays the same. When this swings the other way, going to positive 5 milliamps over, you know, a set current, then this one goes negative 5 milliamps. Again, keeping everybody the same across the entire thing. And it operates from the simple fact of this grid circuit being hooked the way it is. So I hope that answered your question and understanding of it. If you have any more questions, just post them, or anyone else does, and I can go over it a little more in depth and do a little better job of showing waveforms and stuff and everything. But that's really it in a nutshell on how it operates and why it's got gained some popularity and stuff. It's not a perfect circuit by any means, and it wasn't really designed for audio. It was actually designed for sweep circuits. So, but in any case, that's it in a nutshell. So I want to thank everybody for watching. I hope this answers your questions, and if you have any, post them and I'll make another video to try to answer them. So thanks for watching, guys, and I'll see you guys in the next video.